In nuclear physics, beta-decay is a type of radioactive decay in which a proton is transformed into a neutron, or vice versa, inside an atomic nucleus. This process allows the atom to move closer to the optimal ratio of protons and neutrons. As a result of this transformation, the nucleus emits a detectable beta particle, which is an electron or positron. Beta decay is mediated by the weak force. There are two types of beta decay, known as beta minus and beta plus. In beta minus decay, a neutron is lost and a proton appears, and the process produces an electron antineutrino. While in beta plus decay, a proton is lost and a neutron appears, and the process produces a positron and electron neutrino. Beta plus decay is thus also known as positron emission. An example of electron emission is the decay of carbon-14 into nitrogen-14. 14,6C14,7N plus E minus plus nu E. In this form of decay, the original element becomes a new chemical element in a process known as nuclear transmutation. This new element has an unchanged mass number E, but an atomic number Z that is increased by 1. As in all nuclear decays, the decaying element is known as the parent nuclide while the resulting element is known as the daughter nuclide. The emitted electron or positron is known as a beta particle. An example of positron emission is the decay of magnesium-23 into sodium-23. 2312 megagrams 2311 R plus E plus nu E. In contrast to beta minus decay, beta plus decay is accompanied by the emission of an electron neutrino and a positron. Beta plus decay also results in nuclear transmutation, with the resulting element having an atomic number that is decreased by 1. Electron capture is sometimes included as a type of beta decay, because the basic nuclear process, mediated by the weak force, is the same. In electron capture, an inner atomic electron is captured by a proton in the nucleus, transforming it into a neutron, and an electron neutrino is released. An example of electron capture is the decay of krypton-81 into bromine-81. 8136 Kr plus E minus 8135 Br plus nu E. Electron capture is a competing decay process for all nuclei that can undergo beta plus decay. The converse, however, is not true. Electron capture is the only type of decay that is allowed in proton-rich nuclides that do not have sufficient energy to emit a positron and neutrino. Beta-minus decay. In beta-minus decay, the weak interaction converts an atomic nucleus into a nucleus with atomic number increased by 1, while emitting an electron and an electron antineutrino. The generic equation is AZXAZ plus 1x plus E minus plus nu E, where A and Z are the mass number and atomic number of the decaying nucleus, and X and X are the initial and final elements, respectively. Another example is when the free neutron decays by beta minus decay into a proton, Np plus E minus plus nu E. At the fundamental level, this is caused by the conversion of the negatively charged down quark to the positively charged up quark by emission of a W- boson. The W- boson subsequently decays into an electron and an electron antineutrino. Du plus E minus plus nu E. The beta spectrum is a continuous spectrum. The total decay energy is divided between the electron and the antineutrino. In the figure to the right, this is shown, by way of example, for an electron of 0.4 MeV energy. In this example, the antineutrino then gets the remainder, 0.76 MeV, since the total decay energy is assumed to be 1.16 MeV. Beta-minus decay generally occurs in neutron-rich nuclei. Beta plus decay. In beta plus decay, or positron emission, the weak interaction converts an atomic nucleus into a nucleus with atomic number decreased by 1, while emitting a positron and an electron neutrino. The generic equation is AZX-AZ-1X plus E plus nu E. This may be considered as the decay of a proton inside the nucleus to a neutron Pn plus E plus nu E. However, beta plus decay cannot occur in an isolated proton because it requires energy due to the mass of the neutron being greater than the mass of the proton. Beta plus decay can only happen inside nuclei when the daughter nucleus has a greater binding energy than the mother nucleus. The difference between these energies goes into the reaction of converting a proton into a neutron, a positron and a neutrino, and into the kinetic energy of these particles. In an opposite process to negative beta decay, the weak interaction converts a proton into a neutron by converting an up quark into a down quark by having it emit AW+ or absorb AW-. Electron capture. In all cases where beta plus decay of a nucleus is allowed energetically, so is electron capture, the process in which the same nucleus captures an atomic electron with the emission of a neutrino, AZX plus E minus AZ minus 1X plus nu E. The emitted neutrino is monoenergetic. In proton-rich nuclei where the energy difference between initial and final states is less than 2 MeC2, beta plus decay is not energetically possible, and electron capture is the sole decay mode. If the captured electron comes from the innermost shell of the atom, the K shell, which has the highest probability to interact with the nucleus, the process is called K capture. If it comes from the L shell, the process is called L capture, etc. Competition of beta decay types. 3 types of beta decay in competition are illustrated by the single isotope copper-64, which has a half-life of about 12.7 hours. The isotope has one unpaired proton and one unpaired neutron, so either the proton or the neutron can decay. This particular nuclide is almost equally likely to decay through proton decay by positron emission or electron capture, as through neutron decay by electron emission. Helicity of neutrinos, electrons and positrons emitted in beta decay. After the discovery of parity non-conservation, it was found that, in beta decay, electrons are emitted mostly with negative helicity, i.e., they move, naively speaking, like left-handed screws driven into a material. Conversely, positrons have mostly positive helicity, i.e., they move like right-handed screws. Neutrinos have positive helicity, while antineutrinos have negative helicity. The higher the energy of the particles, the higher their polarization. Energy release. The Q value is defined as the total energy released in a given nuclear decay. In beta decay, Q is therefore also the sum of the kinetic energies of the emitted beta particle, neutrino, and recoiling nucleus. Beta particles can therefore be emitted with any kinetic energy ranging from 0 to Q. A typical Q is around 1 MeV, but can range from a few keV to a few tens of MeV. Since the rest mass of the electron is 511 keV, the most energetic beta particles are ultra-relativistic, with speeds very close to the speed of light. Beta minus decay. Consider the generic equation for beta decay AZX plus 1X plus E minus plus nu E. The Q value for this decay is, whereas the mass of the nucleus of the AZX atom is the mass of the electron, and is the mass of the electron antineutrino. In other words, the total energy released is the mass energy of the initial nucleus, minus the mass energy of the final nucleus, electron, and antineutrino. The mass of the nucleus Mn is related to the standard atomic mass m by, that is, the total atomic mass is the mass of the nucleus, plus the mass of the electrons, minus the binding energy by of each electron. Substituting this into our original equation, while neglecting the nearly zero antineutrino mass and difference in electron binding energy, which is very small for high Z atoms, we have this energy is carried away as kinetic energy by the electron and neutrino. Because the reaction will proceed only when the Q value is positive, beta minus decay can occur when the mass of atom AZX is greater than the mass of atom AZ plus 1X. beta plus decay. The equations for beta plus decay are similar, with the generic equation AZ(x)(AZ-1x) plus E plus nu E giving. However, in this equation, the electron masses do not cancel, and we are left with because the reaction will proceed only when the Q value is positive. Beta plus decay can occur when the mass of atom AZX exceeds that of AZ1X by at least twice the mass of the electron. Electron capture. The analogous calculation for electron capture must take into account the binding energy of the electrons. This is because the atom will be left in an excited state after capturing the electron, and the binding energy of the captured innermost electron is significant. Using the generic equation for electron capture AZX plus E minus AZ minus 1x plus nu E, we have, which simplifies to, where Bn is the binding energy of the captured electron. Because the binding energy of the electron is much less than the mass of the electron, nuclei that can undergo beta plus decay can always also undergo electron capture, but the reverse is not true. Nuclear transmutation. If the proton and neutron are part of an atomic nucleus, these decay processes transmute one chemical element into another. For example, beta decay does not change the number A of nucleons in the nucleus, but changes only its charge Z. Thus, the set of all nuclides with the same A can be introduced. These isobaric nuclides may turn into each other via beta decay. Among them, several nuclides are beta stable, because they present local minima of the mass excess. If such a nucleus has numbers, the neighbor nuclei and have higher mass excess and can beta decay into, but not vice versa. For all odd mass numbers A, there is only one known beta-stable isobar. There are about 355 known beta-decay stable nuclides total. Usually, unstable nuclides are clearly either neutron-rich or proton-rich, with the former undergoing beta decay and the latter undergoing electron capture. However, in a few cases of odd proton, odd neutron radionuclides, it may be energetically favorable for the radionuclide to decay to an even proton, even neutron isobar either by undergoing beta positive or beta negative decay. An often cited example is 6429 Cu, which decays by positron emission, electron capture 61% of the time to 6428 Ni, and 39% of the time by beta decay to 6430 zinc. Most naturally occurring isotopes on Earth are beta-stable. Those that are not have half-lives ranging from under a second to periods of time significantly greater than the age of the universe. One common example of a long-lived isotope is the odd proton odd neutron nuclide 4019K, which undergoes all three types of beta decay with a half-life of 7016402990552000001.277 times 109 years. Double beta decay. Some nuclei can undergo double beta decay where the charge of the nucleus changes by 2 units. Double beta decay is difficult to study, as the process has an extremely long half-life. In nuclei for which both beta decay and beta-beta decay are possible, the rarer beta-beta decay process is effectively impossible to observe. However, in nuclei where beta decay is forbidden but beta-beta decay is allowed, the process can be seen and a half-life measured. Thus, beta-beta decay is usually studied only for beta-stable nuclei. Like single beta decay, double beta decay does not change A. Thus, at least one of the nuclides with some given A has to be stable with regard to both single and double beta decay. Ordinary, double beta decay results in the emission of 2 electrons and 2 antineutrinos. If neutrinos are major nanoparticles, then a decay known as neutrinoless double beta decay will occur. Most neutrino physicists believe that neutrinoless double beta decay has never been observed. Bound state beta- decay. A very small minority of free neutron decays are so-called two-body decays, in which the proton, electron and antineutrino are produced. but the electron fails to gain the 13.6 electron volts energy necessary to escape the proton, and therefore simply remains bound to it as a neutral hydrogen atom. In this type of beta decay, in essence all of the neutron decay energy is carried off by the antineutrino. For fully ionized atoms, it is possible in likewise manner for electrons to fail to escape the atom, and to be emitted from the nucleus into low-lying atomic bound states. This cannot occur for neutral atoms with low-lying bound states which already filled by electrons. The phenomenon in fully ionized atoms was first observed for 163 dy66 plus in 1992 by Young et al. Of the Darmstadt Heavy Ion Research Group. Although neutral 163 dy is a stable isotope, the fully ionized 163 dy66 plus undergoes beta decay and decay in L shells with a half-life of 47 days. Another possibility is that a fully ionized atom undergoes greatly accelerated beta decay, as observed for 187 Re by Bosch et al., also at Darmstadt. Neutral 187 Re does undergo beta decay with a half-life of 42 times 109 years. But for fully ionized 187 Re 75+, this is shortened by a factor of 109 to only 32.9 years. For comparison, the variation of decay rates of other nuclear processes due to chemical environment is less than 1%. Forbidden transitions. Beta decays can be classified according to the L value of the emitted radiation. When L greater than 0, the decay is referred to as forbidden. Nuclear selection rules require high L values to be accompanied by changes in nuclear spin and parity. The selection rules for the 50th forbidden transitions are, where delta pi equals 1 or minus 1 corresponds to no parity change or parity change, respectively. The special case of a transition between isobaric analog states, where the structure of the final state is very similar to the structure of the initial state, is referred to as superalloyed for beta decay, and proceeds very quickly. The following table lists the delta J and delta pi values for the first few values of L. Fermi transitions. A Fermi transition is a beta decay in which the spins of the emitted electron and antineutrino couple to total spin, leading to an angular momentum change between the initial and final states of the nucleus. In the non-relativistic limit, the nuclear part of the operator for a Fermi transition is given by with the weak vector coupling constant. The isospin raising and lowering operators, and running over all protons and neutrons in the nucleus. Gamma-Teller transitions. A Gamma-Teller transition is a beta decay in which the spins of the emitted electron and antineutrino couple to total spin, leading to an angular momentum change between the initial and final states of the nucleus. In this case, the nuclear part of the operator is given by with the weak axial vector coupling constant, and the spin Pauli matrices, which can produce a spin flip in the decaying nucleon. Beta emission spectrum. Beta decay can be considered as a perturbation as described in quantum mechanics, and thus Fermi's golden rule can be applied. This leads to an expression for the kinetic energy spectrum N of emitted betas as follows, where T is the kinetic energy, Cl is a shape function that depends on the forbiddenness of the decay, F is the Fermi function with Z the charge of the final state nucleus, E equals T plus mc2 is the total energy, P equals square root 2 minus 2 is the momentum, and Q is the Q value of the decay. The kinetic energy of the emitted neutrino is given approximately by Q minus the kinetic energy of the beta. As an example, the beta decay spectrum of 210 Bi is shown to the right. Fermi function. The Fermi function that appears in the beta spectrum formula accounts for the Coulomb attraction, repulsion between the emitted beta and the final state nucleus, approximating the associated wave functions to be spherically symmetric. The Fermi function can be analytically calculated to be where S equals square root 1 minus alpha 2 Z2, eta equals plus or minus alpha Z, Pc, rho equals Rn, and gamma is the gamma function. For non-relativistic betas, this expression can be approximated by. Other approximations can be found in the literature. Curie plot. A Curie plot is a graph used in studying beta decay developed by Franz N. D. Curie, in which the square root of the number of beta particles whose momenta lie within a certain narrow range, divided by the Fermi function, is plotted against beta particle energy. It is a straight line for allowed transitions and some forbidden transitions, in accord with the Fermi beta decay theory. The energy axis intercept of a Curie plot corresponds to the maximum energy imparted to the electron, positron. With a Curie plot one can find the limit on the effective mass of a neutrino.